Hello everyone, this is Amit Brambhat, and today we are going to go over Week 2, Chapter 3 Data Representation for CS 110 at VCCS. Let me go ahead and share the screen. This slide introduces Chapter 3 Data Representation. Computers work with many different kinds of information, including numbers, text, sound, images, and video. Regardless of the type of data, computers ultimately store and process everything using binary digits or bits. This chapter explores how real-world information is transformed into forms that computers can store, manipulate, and transmit. We'll examine the difference between analog and digital information, understand data compression, and learn how multimedia data such as audio, images, and video are represented digitally. Data representation is fundamental to computing because it defines accuracy, efficiency, and quality of everything a computer handles. By understanding these representations, we gain insights into both power and the limitations of computer systems. We begin by distinguishing between analog and digital information, two fundamentally different ways of representing data. Next, we'll explore data compression, learning what it is, why it's used, and how to calculate compression ratios. We'll also examine how computers represent negative numbers and floating point values in binary format. In addition, the chapter introduces character representation systems, including ASCII and Unicode, which allow text to be stored digitally. Finally, we'll learn techniques for compressing text data. These goals prepare us to understand how diverse types of information are encoded, stored, and transmitted efficiently in computer systems. Here, the chapter goals are by turning our attention to multimedia data. We will explain how the sound works and how it can be captured and represented digitally. We'll also explore how colors are defined using RGB values, and computers represent images and graphics. An important distinction between raster and vector graphics will be explained, showing different images, formats, and how they work. Narration will examine a video representation, including spatial and temporal compression techniques. By the end of this chapter, you'll understand how complex media types, sound, image, and video are reduced to binary form while maintaining acceptable quality for human perception. Here, the slide explains computers are multimedia devices capable of handling many types of information. Computers store, present, and manipulate numbers, text, audio, images, graphics, and video. Although these data types look very different to us, they are all stored internally as binary digits or bits. This uniform representation allows computers to process diverse kinds of information using the same underlying hardware. Understanding that all data reduces to binary helps explain how computers seamlessly switch between tasks like playing music, displaying images, and processing text using the same system. Data in computers, compression. Data compression is the reduction of the amount of space required to store data or the bandwidth needed to transmit it. Compression ratio is defined as the size of compressed data divided by the size of the original data. A lower ratio means better compression. Compression techniques fall into two categories. Lossless compressions allows the original data to be perfectly reconstructed, while lossy compression sacrifices some information to achieve higher compression. Lossy methods are often used for images, audio, and video where minor loss is acceptable. Compression is essential for efficient storage and fast transmission of large multimedia files. Analog and digital information. How do computers, which are finite systems, represent an infinite and continuous world? The answer is that computers do not attempt to represent reality perfectly. Instead, they represent enough of the world to satisfy our computational needs and our sense of sight and sound. By sampling and approximating real-world phenomena, computers can store and process information efficiently. This idea underlies all digital media. Whether we are working with sound, images, video, computers can capture discrete measurements that approximate continuous reality. Understanding this limitation helps explain why digital representations are approximations and why some loss of detail is often inevitable. The two fundamental ways information can be represented are analog and digital. Analog data is continuous and changes smoothly, closely mirroring the physical phenomena it represents. Examples include sound waves and temperature. Digital data, in contrast, is discrete. It breaks down information into separate distinct elements that can be counted and stored. Computers rely on digital data because discrete values can be represented reliably using binary numbers. This distinction is critical in computing, as it explains why real-world analog information must be converted or digitized before a computer can process it. This slide shows mercury thermometer as a classic example of an analog device. As temperature changes, mercury rises or falls in a small, smooth, continuous manner. There are infinitely many possible positions that mercury can occupy, reflecting the continuous nature of analog information. While this makes analog devices intuitive for humans, it presents challenge for computers, which cannot easily store or process continuous values. This example helps us illustrate why digital systems rely on approximations rather than exact analog representations. Here we see why computers convert analog data into digital form. Since computers work best with discrete values, analog data must be digitized. Digitization involves breaking continuous information into individual pieces and representing those pieces separately. A key question posed here is why binary is used for digitized data. The answer lies in reliability. Electronic circuits can easily and consistently distinguish between two states. Binary representation allows digital systems to efficiently store, process, and transmit information while minimizing errors caused by noise or signal degradation. This slide introduces important facts about electronic signals. An analog signal fluctuates continuously in voltage, reflecting the changes in the data it represents. A digital signal, on the other hand, has only two stable states, high and low, corresponding to binary digits, 0 and 1. Both types of signals degrade as they travel through a transmission medium due to environmental interferences and noise. Understanding signal behavior is essential for appreciating why digital communication is more robust than analog communication in modern computer systems. This slide explains how digital signals remain reliable over long distances. Over time, even digital signals degrade and lose their precise shape. To address this, digital systems periodically reclock the signal, regenerating it to restore its original form. This process is crucial for maintaining data integrity during transmission. Analog signals, by contrast, accumulate noise continuously and cannot be easily restored. The fundamental difference explains why modern communication systems overwhelmingly favor digital signals. Binary representations. Here we explore how bits represent information. A single bit, which can be 0 or 1, represents two possible values. Two bits can represent four possibilities, and this pattern continues exponentially. The slide challenges us to consider how many values 3, 4, or 8 bits can represent. In general, n bits can represent 2 raised to n distinct values. This exponential growth is a cornerstone of computing and explains how relatively small numbers of bits can represent vast amounts of information. Here we have a slide that shows what previous slide asked for. These are the bit combinations for 1, 2, 3, 4, and 5 bits. These different bit combinations and how they map to distinct values is seen here. Each unique pattern of zeros and ones represent a unique number of symbol. The figure reinforces the idea that increasing number of bits dramatically increases the number of representable values. This concept is central to memory design, character encoding, and numerical representation. Understanding how bit combinations work helps explain storage limits and the relationship between bit length and representational capacity. This slide asks us some questions on binary representations. Power of 2 growth. How many bits are needed to represent a given number of items, and highlights the exponential nature of binary representation. Each additional bit doubles the number of possible values. This doubling affects why computer capacities such as memory size and address space grow in powers of 2. Recognizing this pattern allows us to predict how much storage is needed for a given task, and why system limits often appear as powers of 2. Representing natural numbers. Here we focus on how computers represent natural numbers in binary form. Natural numbers are converted into binary and stored using a fixed number of bits. Because storage units have a fixed size, leading zeros may be added to ensure consistent length. The slide also prompts us to think about what integers include the natural numbers do not, namely negative values. This distinction sets the stage for the next series of slides, which explores how computers represent negative numbers efficiently. Revisiting negative values. Signed magnitude. The signed magnitude method for representing negative numbers, which is commonly used by humans. In signed magnitude representation, one bit is used to indicate the sign of number, positive or negative, while the remaining bit represents the magnitude or distance from 0. This mirrors how we think of numbers on a number line, with negative values appearing before positive ones. Though intuitive, signed magnitude is not well suited for computers because it creates complications when performing arithmetic operations and introduces redundant representation. This slide provides the conceptual starting point for understanding how computers evolve more efficient techniques for representing negative numbers in binary. two zeros problem. The slide highlights a major drawback of signed magnitude representation: the existence of the two zeros, positive 0 and negative 0. While this is not an issue for humans, it introduces unnecessary complexity in computer hardware and software. To solve this, computers instead associate integers with natural numbers. Half of the representable values are used for non-negative numbers, and the other half represent negative numbers. This approach eliminates the redundancy of two zeros and simplifies arithmetic operations. This slide explains why computers-friendly numeric representations sometimes differ from human-friendly ones. Numerical mapping. Here we see how negative numbers can be represented by mapping them onto a range of natural numbers. Using two decimal digits as an example, values from 0 through 49 represent non-negative numbers, while values from 50 through 99 represent negative numbers. This circular numbering scheme allows arithmetic operations to wrap around, enabling negative values to be represented without a separate sign bit. The number line shown visually demonstrates how numbers can transition smoothly from positive to negative. This conceptual model prepares us for understanding complement-based numeric representation. Addition. Here we see how addition works under this mapping scheme. To add two numbers, we simply add their representations and discard any carry that exceeds the allowed number of digits. This works because the numbering system wraps around naturally. The slide invites you to try an example to see how subtraction and addition behave differently under this system compared to signed magnitude representation. This illustrates that the chosen representation directly impacts how arithmetic operations are performed inside a computer. Subtraction. This slide shows how subtraction can be performed using addition by applying the rule a minus b equals a plus negative b. In complement-based representation, computing the negative of a number is straightforward and well-defined. This makes subtractions no more complex than addition. This example shown encourages hands-on practice and reinforces the simplicity gained by using the complement systems. This approach is one of the main reasons why modern computers rely on complement representations rather than signed magnitude. Tens complement. Tens complement is used here as a conceptual stepping stone to binary two's complement. In tens complement, a negative number is represented by subtracting its magnitude from the base raised to the number of digits, in this case 100. For example, negative 3 becomes 97. This numeric trick allows subtraction to be replaced with addition. The slide challenges us to think about how this idea translates into binary, setting the stage for two's complement representation. Two's complement. The dominant method computers use to represent negative integers. In two's complement, the leftmost bit indicates sign, but unlike signed magnitude, it also contributes to the value. Negative numbers are represented by inverting the bits and adding 1. This system eliminates the dual zero problem and allows addition and subtraction to be handled using the same circuitry. The slide's vertical number line helps visualize how positive and negative values are arranged in binary. Overflow. Arithmetic in 2's complement behaves similarly to 10's complement. Addition and subtraction are performed the same way for positive and negative values. However, a limitation arises when the result of computation exceeds the number of bits available. When this happens, overflow occurs, producing an incorrect result. The example shown demonstrates what happens when values fall outside the representable range. This highlights the limits imposed by finite storage in digital systems. Number overflow. Here is a concrete example of overflow